So this week you sent over some material that's pretty mind-blowing. It suggests that dark matter, the cosmic ghost that makes up most of the universe's mass, might not be so invisible after all. Which is a pretty wild thought. Could we
Yeah.
have already unknowingly encountered, its fingerprints?
Right.
Let's dive into whether some strange signals from our galaxy's core could be just that.
That is the fascinating question we're going to be tackling.
Okay.
Dark matter, this mysterious substance that accounts for about 80% of the universe's mass.
Right.
It's been incredibly elusive.
Yeah.
It doesn't interact with light, so we can't see it directly.
Right.
The only way we know it's there is through its gravitational effects, like the unexpectedly rapid spin of galaxies,
Right.
or the bending of light around massive structures, a phenomenon known as gravitational lensing.
Yeah, it's like this unseen framework shaping the cosmos.
Exactly.
And while the big hunt has been on for direct encounters with dark matter particles, the material you shared proposes a fascinating twist. Perhaps we've already witnessed its handiwork just indirectly
Right.
through some peculiar astronomical observations we haven't fully deciphered yet.
Interesting.
Specifically, it points to some oddities happening right in our galactic backyard in the central molecular zone.
Okay.
So what's the core mystery there?
Well, what's particularly intriguing is this puzzle that's been around for about a decade. Scientists have been picking up a peculiar infrared signal emanating from this incredibly dense and energetic region.
Okay.
More precisely, they've detected an unexpected absorption of infrared light.
Okay.
Now, typically, the dominant form of hydrogen out in space is H-rose, two hydrogen atoms joined together.
Right.
And the crucial thing is that H doesn't readily absorb infrared light. You generally need molecules with a more complex structure capable of vibration to do that effectively.
Okay, so if the usual cosmic hydrogen isn't the culprit, what's causing this infrared light to get absorbed? The material mentions a specific molecule that's popping up in surprisingly high concentrations.
Precisely. They are finding an overabundance, 100-fold more than what standard models predict,
Wow.
of HO molecules.
Okay.
That's 3 hydrogen atoms with a positive charge, having lost an electron.
Okay.
This molecule can absorb infrared light.
Mm-hmm.
So the big question hanging in the air is, why is there so much of it clustered in this specific area?
Right.
Our standard understanding of astrophysics simply doesn't account for these levels.
Which leads us to the really juicy part, the potential dark matter link.
Yes.
This new idea suggests that this surplus of HO might be a consequence of dark matter particles doing their thing.
Exactly.
So tell us more about these proposed dark matter particles and how they could be boosting the formation of this 3-hydrogen molecule.
So the hypothesis focuses on a particular type of dark matter particle,
Okay.
one with a medium mass in the MeV range.
Meh.
Yeah, roughly 1 million electron volts,
Okay.
which places it in a less explored energy range than those targeted by our most powerful particle detectors.
Got it.
This mass range is interesting because these particles will be too light to be easily snagged by high-energy experiments like the LHC,
Okay.
and too heavy for the detectors specifically designed to hunt for ultralight axion particles.
Mm-hmm.
So this middle ground has been somewhat less scrutinized.
Interesting.
The core idea is that within the crowded environment of the galactic center, these medium-mass dark matter particles could be colliding and annihilating each other.
Okay, so dark matter particles bumping into each other and vanishing. What happens then?
Well, not exactly vanishing without a trace.
Right.
Their annihilation wouldn't erase energy, it would release it in a different form,
Okay.
specifically as other particles.
Got it.
Primarily electrons and their antiparticles, positrons.
Okay.
These newly created charged particles would then interact with the surrounding hydrogen gas.
So these energetic electrons and positrons were like tiny cosmic bowling balls crashing into the hydrogen molecules.
That's a great analogy.
Thanks.
They would ionize the hydrogen, essentially knocking electrons off the HRO molecules.
Got it.
This ionization process then kicks off a series of chemical reactions that ultimately leads to the formation of more HO. So the more dark matter annihilation events, the more electrons and positrons, the more ionized hydrogen, and consequently, the more of these infrared-absorbing HO molecules we observe.
It's a pretty elegant and compelling explanation for this decade-old mystery.
I think so.
It definitely weaves together these disparate threads in a surprising way.
Yeah.
But the material also touches on another cosmic puzzle that this same dark matter annihilation idea might illuminate. something about a specific type of gamma ray.
Yes, and this is where the narrative gets even more interesting.
Yep.
Since the 1970s, astronomers have consistently detected a specific signature of gamma ray emission.
Mm-hmm.
It's a sharp spike in energy at 511 keV,
Okay.
originating from the galactic center.
Got it.
The generally accepted explanation for this is the annihilation of positrons with electrons.
Okay.
When these antiparticles meet, they annihilate, converting their mass into energy. This energy takes the form of 2 gamma-ray photons,
Okay.
with that characteristic 511 keV energy.
So the crucial link here is that the same dark matter annihilation events proposed to be generating the XSA show would also be spitting out these positrons.
Precisely.
Okay.
If medium mass dark matter particles are indeed annihilating in the manner we've discussed,
Right.
the resulting cascade of particles wouldn't just include electrons, but also positrons. These positrons would then journey through the galactic center, eventually encountering electrons and annihilating,
Right.
producing the observed 511 keV gamma-ray line.
Got it.
So this theory offers a unified framework for understanding 2 seemingly independent phenomena:
Okay.
the overabundance of age-absorbing infrared light and the persistent presence of this specific gamma-ray signature.
It paints a very neat picture, this idea that a single fundamental process could be the underlying cause of these 2 distinct signals we're detecting.
It's a pretty exciting possibility.
But the material also wisely cautions against jumping to conclusions. Yes.
Reminding us of past instances where what looked like dark matter turned out to have more conventional explanations.
It's important to be cautious.
Totally.
The history of dark matter research is littered with examples where promising initial findings sparked excitement, only to later be attributed to more ordinary astrophysical sources.
Yeah, like what?
Well, for instance, the observed surplus of positrons in cosmic rays. That was initially considered a strong hint of dark matter annihilation.
Okay.
But now, many scientists believe it's more likely due to sources like supernovae
Right.
or active galactic nuclei, AGN.
Got it.
Similarly, some high-energy cosmic rays that were once flagged as potential darkest signals might actually originate from rapidly spinning neutron stars called millisecond pulsars.
Interesting.
So yeah, we need to keep our feet on the ground.
Absolutely, no matter how enticing the story sounds.
Right.
So what would be the key piece of evidence needed to really bolster this new hypothesis and firmly connect these infrared and gamma-ray signals to dark matter? The next vital step involved meticulously mapping the spatial distribution of these signals.
Okay.
If this theory holds true,
Right.
the observed patterns of infrared absorption and the 511 keV gamma-ray emission should closely mirror the predicted distribution of dark matter density within the Milky Way's core.
Got it.
We have theoretical models that suggest dark matter should be more densely concentrated towards the galactic center.
Right.
If the regions exhibiting the strongest infrared absorption and gamma-ray emission precisely overlap with these high-density dark matter zones, it would provide significantly stronger support for this hypothesis.
That makes perfect sense. If dark matter is indeed the engine driving these effects, then the signal should be most intense where the dark matter is most packed together.
Exactly.
It's like tracing smoke back to the fire. You'd expect the heaviest smoke right above the flames.
An excellent analogy.
And looking beyond the specific science here, the material you shared also touches on some broader themes.
Yeah, like what?
This whole discussion highlights how exciting it is when different pieces of the cosmic puzzle might fit together.
Definitely.
And,
you know,
speaking of engaging with these kinds of ideas, platforms like Brilliant, they really emphasize the importance of interactive science learning.
for sure.
It's a good reminder that even when we're wrestling with the most profound mysteries of the universe,
Right.
there's still a playful and engaging aspect to scientific exploration.
Absolutely.
So to bring it all together for you,
Okay.
the core takeaway is this tantalizing possibility that we might have already stumbled upon indirect evidence of dark matter. Through these peculiar infrared and gamma-ray signals emanating from the heart of our galaxy.
Right.
And the proposed mechanism involves medium mass dark matter particles annihilating, setting off a chain reaction that leads to an excess of HU molecules and the emission of those characteristic gamma rays.
That's a succinct and accurate summary.
Awesome.
It underscores the idea that sometimes the most significant discoveries might be lurking in plain sight.
Yeah.
Hidden within anomalies that we haven't yet fully grasped.
Right.
This new perspective encourages us to revisit existing astronomical data with fresh eyes
Oh.
and to consider unconventional explanations.
I like that.
Yeah.
So here's a final thought to ponder.
Okay.
If this seemingly unusual infrared signal is indeed a fingerprint of dark matter, what other seemingly ordinary astronomical observations might be harboring equally profound secrets about the universe? Just waiting for us to develop the right interpretive lens.
That's a great question.
It really makes you wonder what else we might be overlooking, hidden within the vast data sets we already possess.
Definitely. Lots to think about.
Thanks for joining us for this deep dive.
My pleasure.